And welcome back. As we continue our cosmic journey, we of course are now moving on to where we can start looking at the evolution of stars as they start moving from the main sequence into that of their red giant phase. So let's first start off by recapping the main sequence and how it is a state of equilibrium. If you recall, once a star has reached the main sequence stage of its life, it derives its energy almost entirely from the conversion of hydrogen to helium via the process of nuclear fusion deep within its core. Since hydrogen is the most abundant element in stars, this process can maintain the star's equilibrium for quite a long time. Thus, all the stars remain on the main sequence for most of their lives. Now, if we look at the HR diagram, we'll notice that the left-hand edge of the main sequence band in the HR diagram is kind of unique because we see a lot of stars that are kind of approaching what we call the zero-age main sequence. We use the term zero-age to mark the time when a star stops contracting, kind of settles on into the main sequence, and actually begins to fuse hydrogen within its core. Now, the zero-age main sequence is a continuous line in the HR diagram that shows where stars of different masses but similar chemical composition can be found when they begin to fuse hydrogen. Now, since only about 0.7% of the hydrogen used in fusion reactions is actually converted to energy, fusion does not necessarily change the total mass of the star very appreciably during this long period. It's a very stable process. Yes, we are losing a little bit for the conversion of energy, but gradually most of that hydrogen will remain. As we've seen when we looked at the proton-proton chain reactions, some of that, of course, is going to give us back hydrogen that can then be recycled and used in future reactions. Now, this does, of course, change the chemical composition within central regions where nuclear reactions occur. Even though we are getting some hydrogen back, over time, the hydrogen is gradually going to be depleted. We, of course, are at a net loss here. And we're going to notice that helium is going to take its place. It's going to accumulate deep within the core. Now, this change of composition changes, of course, the luminosity, it changes the temperature, the size, and the interior structure of the star itself. Now, when a star's temperature and luminosity are beginning to change, this is the point that represents the star in the HR diagram where it's going to actually move out of the zero-age main sequence. Now, the calculations show that the temperature and density in the inner region actually are going to slowly increase as the helium accumulates within the center of a star. As the temperature gets hotter, each proton acquires more energy of motion on average. Protons are thereby more likely to interact with other protons, and our rate of fusion is actually going to increase. Now, if the rate of fusion goes up, that means that our rate at which energy is being generated is also going to increase, and the luminosity of the star is going to gradually rise because, again, we have more fusion, which is making more energy. Now, initially, these changes are going to be very small, and the stars are going to remain within the main sequence band, again, most of their life. And so even as this change starts to happen, it's still not going to be something that we notice right away. However, we do have different lifetimes as we look at the main sequence. How many years a star remains in the main sequence band actually really depends on its mass. And now, does that mean we're going to have different things for smaller stars versus larger stars? Well, you might think that if we have a more massive star, we have more fuel. And if we have more fuel, that star can last a lot longer. But the truth is, it's not that simple. The lifetime of a star in a particular stage of evolution really depends on how much nuclear fuel it has and how quickly it's going to use that fuel. Now, as a general rule of thumb, we're going to find that more massive stars use their fuel much more quickly than the mass of a lower star, which again seems a little weird, but there's a reason for this. The reason massive stars age quickly is that the rate of fusion depends very strongly on the star's core temperature. And what determines how hot a star's central region can get? Well, it's the mass. As the massive star has a higher mass, this is going to require naturally higher pressure to balance it out, which in turn is going to be produced by higher temperature. The higher the temperature that we have deep within the star's core, well, the faster it's going to race through the storehouse of central hydrogen. And though massive stars have much more fuel, and you would think that that means they can last longer, because of their size, they actually burn faster through that fuel supply in their lifetimes, and they actually end up being shorter than those we find in their low mass counterparts. And so if we look at this table here, we can actually see a couple different spectral types of stars. We can, of course, see their surface temperature, their mass in relation to the mass of our own sun, and their lifetime on the main sequence. So, for example, if I look at an O5 star, you can see that it has a very high surface temperature, about 54,000 Kelvin. The mass is about 40 times the mass of our sun. So, again, we have a very high temperature to correspond to the very high mass. The trade-off is that if we look at its lifetime on the main sequence, we can see it's only about 1 million years. And because it's only about 1 million years, I mean, this is a very short lifespan. If we compare that to, let's say, an M0 star, we can see that its surface temperature is about 3750. That mass is only about 0.4 times the mass of our sun. And you can see that it spends a whopping 200 billion years on the main sequence, which is very different from our sun. If we look at this G0 star, which is very close to our own sun, you can see its surface temperature is about 6,050 Kelvin. The mass is 1.1 times the sun, so it's slightly larger, and its lifetime is going to be about 9 billion. So our own sun would be somewhere pretty close to these values here that we can see here. So what happens when we start moving out of the main sequence? Well, the next stage that we would expect is the red giant stage. Eventually, what happens is all the hydrogen in a star's core, where the core, of course, is the only place that's really hot enough for reactions to occur, that core is going to use that fuel up. Because that hydrogen core no longer has hydrogen, well, energy can no longer be generated by hydrogen fusion within the stellar core. And so now we have to move to the fusion of helium. Well, the fusion of helium requires much higher temperatures. And since the central temperature at the star's current size and everything like that is not high enough to fuse helium, well, there's not any nuclear energy source really to supply the heat to that central region of the star. So we now have the end of our long period of stability where we just were fusing hydrogen, fusing hydrogen, fusing hydrogen, and gravity is again going to kind of take over. So what's going to happen is the core will contract. As the star's core shrinks, well, the energy of the inward falling material is converted to heat. So we have that gravitational contraction that is now happening. So when we have gravitational contraction, it's important to remember that the heat that we generate, much like all heat, is still going to flow outward to where it is a bit cooler. In this process, the heat is going to raise the temperature of a layer of hydrogen that has spent the whole long main sequence time just outside the core. Now, this hydrogen was almost but not quite hot enough to undergo fusion and really take part in the main action that sustains the star that we saw previously. It wasn't quite to that temperature. But now because we are contracting that core, we've produced additional heat, which allows the hydrogen to kind of go over the limit, and we actually get a shell of hydrogen nuclei that are just outside the core that are now hot enough for hydrogen fusion to begin once again. And if we take a look at these two diagrams, we can really kind of get a view of what this is actually talking about. So during the main sequence, a star has a core where fusion takes place, and we've got a much larger envelope that's simply just too cold fusion. Yes, the hydrogen is very warm, but it's not at the temperature required for fusion. As we can see here, we have our sterile envelope, and then we have the hydrogen burning core. However, when we begin that change where the hydrogen in the core is exhausted and it's now made of helium instead of hydrogen, we can see that the core has been compressed by gravity and is now heating up. This additional heat starts hydrogen fusion in a layer just outside the core. And this is going to have a very big consequence on the star itself. Now, most stars generate more energy each second when they're fusing hydrogen in the shell surrounding the helium core than they actually did when the hydrogen fusion was confined to the central part of that star. Therefore, these stars are going to increase in luminosity because, of course, they're generating more energy, right? Well, with all the new energy pouring outward, the outward layers of the star actually begin to expand. and the star is eventually going to grow and grow until it reaches enormous proportions. As we can see here in this example, we can see our own sun, just for context, and we can see two other stars that are, of course, moving into their red phase, and you can see how much larger they are simply in comparison to our sun, which is still on the main sequence. Now, this, of course, is going to give us some models for the evolution to the giant stage. If we look at our H-diode diagram, the star leaves the main sequence band and then will move upward, or brighter, and to the right, which is a cooler surface temperature. Now, the expansion of a star's outer layers causes the surface temperature to decrease. And as it cools, the star's overall color is going to make it become much redder. The star is also simultaneously becoming more luminous, so it's brighter, but it's also cooler. Now, over time, these massive stars are going to become red, either supergiants, or the lower mass stars like our own sun will simply just become red giants. Now, red giants, of course, can become so large that if we were to replace the sun with one of them, its outer atmosphere is actually going to extend to the orbit of Mars or even beyond. This is the next stage in the life of a star, as it kind of moves from the period of youth and adulthood into kind of the old age. If we consider the relative ages of, let's say, the sun and the star Betelgeuse, we actually can see that this idea of big stars die faster is very true. Betelgeuse is a mere 10 million years old, which is relatively young compared to our sun's 4.5 billion years. But if we look at Betelgeuse, we can see it's already nearing its death throes as a red supergiant, and that's again because it is much more massive. And if we look at this HR representation of this lifespans, we can take a look here at the solid black lines, which show the predicted evolution from the main sequence through the red giant or supergiant stage. Now, each track is, of course, labeled with the mass of each star it's describing, and the numbers show how many years each star takes to become a giant. And the red line, of course, is the zero-age main sequence. The more massive the star, we'll find the shorter time it takes for each stage in life. So, for example, if we look at the 15 solar mass star right up here, we can see here is our zero-age line right here. And this is 1.01 times 10 to the 7th, 1.11 times 10 to the 7th, etc. But if I were to go down here to a smaller star, let's go ahead and look, for example, at one solar mass, which is very similar to our own. We can see this is 7 times 10 to the 9th, 10.4 times 10 to the 9th, etc. So you can see this is a much smaller number compared to this, because this is in billions, whereas this is in millions.